Thank you, Kelly. Hello, everyone. Good afternoon, good morning, or good evening, depending on where you are joining us today. Thank you all for registering and participating in this webinar. My name is Leila, and I have Kelly Lass with me, and we are your hosts today. And Kelly will moderate the Q&A sessions. This webinar is sponsored by the Center for the Study of Ethics in the Professions. The topic of our webinar is machine learning fairness. Today we have Dr. Gilpin and Dr. Weinberg with us, who are the subject matter experts on this topic. And as Kelly mentioned, we are recording this meeting so we can share it with people who are interested in this topic but could not join us today. In recent years, machine learning algorithms have become widespread in our daily lives. They perform a wide spectrum of tasks, from recommending products to predicting loan approvals. However, as these algorithms have become more ubiquitous, concerns about their fairness and potential biases have also grown. As we rely more on algorithms to make decisions, it's essential to ensure that they do not discriminate against certain groups or reinforce existing inequalities. In this webinar, it is our aim to explore the issue of machine learning fairness, and our speakers will provide insights into how we can develop more equitable algorithms that promote fairness and social justice, and what are the potential and actual barriers and obstacles along the way. So our panel of experts, Dr. Gilpin and Dr. Weinberg, will discuss current trends, challenges, and best practices in machine learning fairness, and share their experiences and insights on the topic. We have two invited speakers, so we will have two presentations. Each presentation will be followed by a short question and answer session right after it. We will start with Dr. Gilpin. Dr. Leilani Gilpin is an assistant professor in Department of Computer Science and Engineering and at UC Santa Cruz. Her research focuses on the design and analysis of methods of autonomous systems to explain themselves. Her work has applications to robust decision-making, system debugging, and accountability. She holds a PhD in computer science from MIT, a master's in computational and mathematical engineering from Stanford University, a bachelor's in mathematics, bachelor's in computer science, and music minor from UC San Diego. Outside of research, Leilani enjoys swimming, cooking, hiking, and org mode. In this webinar, Dr. Gilpin will talk about how explanations can be used for ensuring fairness and accountability. We are really grateful to have her here today, and without further delay, I turn the podium over to Dr. Gilpin. Dr. Gilpin, the floor is yours.
Great, thank you. Thanks for the invitation and the lovely introduction. I'm really excited to be here today. Let's see. Can everyone see my slides? And it's the right.
Yes.
Perfect. So hi everybody. I'm Leilani Gilpin, assistant professor at UC Santa Cruz, and today I'm going to be talking about explainable AI and particularly how that can be used for fairness and accountability. So talk agenda, I'm just going to give a brief introduction to myself. I'm an extremely interdisciplinary scholar. I know that there are a lot of different audience members today, so I'll talk a little bit about my background and sort of where I'm coming from and some of these ideas. Then I'll talk about motivating the problem, which is that systems are imperfect. I'll define what explainability is. I'll talk about what's actually being explained, and I'll talk about that within the lens of fairness and accountability and why that matters. And then also, how do we evaluate explainability, especially when we're using this for safety critical, mission critical decisions? And then I'll use that to talk a little bit about how do we explain critical systems, especially when they need to be accountable and they need to be fair. I'll talk about this specifically in the lens of autonomous vehicles. That's where I do a lot of my research. But these are really useful for any type of application, regardless if that's a computer vision system or a complex system like a self-driving car. I'm also happy to be interrupted. So if people have questions, feel free to interrupt me. Just let me know. So before I start, I just thought I would say hello. So this is me. I'm Leilani. I got my bachelor's from UC San Diego. This is a picture of me graduating many, many moons ago. And then I got my master's from Stanford, and my PhD was in EECS from MIT. I also sat in a policy lab when I was at MIT, so I have a sort of rich background in thinking about the technical problems, but also the implications to society. I've also spent several years in industry. So I worked for a couple of years at Xerox PARC between my master's and my PhD. I also worked in France for a while at Imria. And most recently, I worked on Sony AI's team working on explainability for some of their AI agents, including the ones that were playing in Gran Turismo. And my research is all about the methodologies and technologies for complex systems to explain themselves. And I largely think about that, again, through the sort of societal lens. How is this fair? How do we use explanations to ensure fairness? How do we use that to ensure accountability? And one of the best examples that I think about why this work matters is to actually look at self-driving cars. And in fact, if we look at complex systems, which I'm calling a system that's made out of multiple parts, they really do fail in these types of complex ways. So I love to give these types of talks because there are always new self-driving car failures that I get to talk about. So this is one, this is a self-driving race car, and this is what happened in its second public trial. Hopefully everyone can see the video. I'll play it one more time, and then I'm curious from the audience what people think happened here. Does anybody have an explanation of what might have happened in this instance?
And feel free to put your answers in the chat. So it saw a white line in front of it and swerved?
Saw a white line in front of it and swerved. Actually pretty close. Any other ideas? And then I'll reveal the answer.
Detected an obstacle?
Detected an obstacle, also very close. So what I think is most interesting about this example is once I explain to you what happened, it's very, very obvious. So what actually happened in this case was that the steering was set to not a number, or NaN. I'm sure many of you have had this in your code before. And because it was set to something not a number, it chose to take the default action, which is to go completely to the right, right? That's kind of unfair, right? Like the default action shouldn't be to go completely to the right, and we have to have better ways to explain these types of modules. So this is a really great example of why we want to make sure that we have good default behaviors and we have better monitoring and explanatory tools. Complex systems can also fail in ways that a human never would. This is an example of a Tesla self-driving car, and you'll see that here it thinks that there's a yellow light, but it's really the moon. An example of something that would never happen to us when we're driving. However, you can imagine the types of repercussions that would occur if indeed the self-driving car thought that this was a yellow light and started slowing down on what is, a high speed area. There have also been issues where self-driving cars, especially Teslas, will actually slow down in front of tunnels. This is related to one of the questions or one of the answers that someone said in the chat, which is that when it sees this contrast, so when it sees a contrast between, the dark shadow of the tunnel versus the lighter part before it, they actually start to slow down. And this has actually caused an immense amount of accidents. So we really want to make sure that they have these types of explanations to be able to learn from their mistakes in these types of critical situations, because these are causing huge amounts of accidents. It should be no surprise that there are adversarial examples. So this is what happens when you add a little bit of noise to an image, but you can also do this in the physical world. So with just a few pieces of tape, all of a sudden the self-driving car thinks that this stop sign is now a 45-mile-per-hour sign. You can imagine, again, the type of ramifications that that would cause for not just the vehicle that you're in, but also the cars around it. And finally, what I'm going to really use to sort of motivate this talk is the issues of predictive inequality. So what do I mean by that? I mean that many of you are probably familiar that there are huge biases in computer vision systems. So for example, computer vision systems are better at detecting faces with lighter skin tones than those of darker skin tones. That's been shown by many wonderful scholars like Timnit Gebru. However, the big issue that was outlined in this paper was that when that same technology is put on a self-driving car, then it becomes that the self-driving car is better at predicting pedestrians with lighter skin tones and darker skin tones. So it's causing harm to, underrepresented people, and that's really not okay. They have no way to explain, and currently we don't really have the types of ways to fix it. But this is part of a much bigger problem, which is that we really have a societal need for explanation. Amazon scrapped its secret AI recruiting tool several years ago because it showed bias against women. Why did that happen? Because the machine learning classifier was basically learning the trend of the data it saw before it. And most of the resumes that it was getting were from men. This also happens in credit decisions. So a lot of the AI fueled credit formulas that we see for figuring out whether you should get a loan or not, again, they are all backed up by data sets that are not very representative. And that's exactly what these machine learning classifiers are learning. So for us, when we're thinking about ways that we can make these machine learning algorithms more fair, ways that we can make them more accountable, I argue that the main way we should do that is to have the ability for these systems to explain. So if that is my argument and that is my thesis, then we have to define, okay, what is explainability? Well, explainability really came into light pretty recently when there was a call for proposals from DARPA, which is the main defense funder, saying that we really need explainable AI. And they described explainable AI as the following. You have an image classification system. So it's taking an image of a cat, it's putting it through some type of deep neural network that you see here. It gets the explanation, okay, this is a cat. But what they really want is an XAI explanation. They want to say that this is a cat because it has fur and it has whiskers and claws and it has these pointy ears, and they can sort of point to what those are. However, I argue that that's actually not exactly right. What we really did in this work and what I've been doing in my work is really taking inspiration from philosophy. This is from Sylvan Bromberger, who wrote a book on explanations called On What We Know We Don't Know. And what he said is that explanations express the answer to not just any questions, but to questions that present the kind of intellectual difficulty. That means that you're actually learning something from the explanation. You're not just reiterating something that you already know. And again, this is extremely important when we think about these opaque machine learning systems, these deep neural network systems that are making decisions and they are not able to explain why. In fact, we don't understand at all what these deep neural networks are doing, right? They're completely not understandable. And in fact, their training process is not understandable. What you basically have is some input that's usually in the form of images or some type of multimodal data. Then you have some middle hidden layers and you get some type of output. And what we know as computer scientists, as machine learning people, as AI experts, is that whenever you're doing something correct, so whenever your classifier is doing fairly well, then whatever you did in the middle, you're just going to do more. And then whenever you're wrong, so whenever your classifier is not getting good accuracy, then just kind of decrease what you're doing in the middle. And again, there's no, knowledge or intellectual difficulty that's being shown in these types of explanations. And so something that we really wanted to do in this research was actually give a review of explainability and then think how that could be used for these types of societal issues. So I'm going to be giving a very high level overview of this large review paper that we did in explainability and then talk why it matters. We gave definitions, we defined a taxonomy. We did that by doing a survey of literature, not just in computer science, but also in artificial intelligence and also philosophy. We provided recommendations for evaluation, especially for these critical systems. And then we talked a little bit about how these explanations can be important for society. So let's start by defining what does it mean to be an explanation? Well, the first thing that we did, and I should say this is fairly controversial, but I think especially thinking about this for fairness, especially thinking about this for accountability and societal issues, it's very important to differentiate what it means to be explainable versus what it means to be interpretable. And again, this is a hot topic. This is the definitions that I'm using, and I'll talk about why I think it's important. Interpretability describes the internals of a system, like a deep neural network, in a way that is understandable to humans. Okay, so an interpretable explanation could be something like a heat map, sort of showing the part of the image that's important, but that is not the same as being complete. Completeness describes the operation in an accurate way. That says, hey, I know that you didn't get your loan, and the reason you didn't get your loan is this part of the algorithm right here. And we argued that an explanation really needs both. If I am to tell you that I have an explanation for my deep neural net system that is deciding whether you get a loan or not, I better be able to describe that in a way that you understand, in a way the users understand, but it also needs to be in a way that's accurate to the underlying model. And that's really the key point of what an explanation is. However, if we look at what we have, in sort of the space of explainability, largely we don't really see that explainability suffices both of these claims. We either have visual cues, so that is where we sort of highlight the individual parts of the image that were important. For example, in this picture of a dome, it's sort of highlighting the top dome part, or if it thinks it's a palace, it's going to highlight the entire part of that image. We have things that are looking at the roles of individual units. So it's sort of decomposing one of the underlying deep neural network systems into sets of vectors, into sets of neurons. And what it's doing there is it's basically highlighting the parts where those neurons or those vectors were important. So it's looking at the particular part of the image that was basically being used for that particular part of the network. Or we have systems that are attention-based. What I mean by attention-based is they're sort of combining these visual cues, also sometimes called saliency maps, with additional information like a textual justification. What's important about this is that when we're adding text to these images, that's not actually describing what the deep neural network is doing. It's just another process on top of image detection. And so if we look at sort of this landscape, so these are largely like the three main parts of explainability that we're looking at. What we have is that these visual cues are interpretable, right? You can understand them. You can sort of, once I explain to you what's actually being explained, you can say, yes, that's definitely interpretable, but it's not complete. It actually doesn't point to the parts of the deep neural network or the opaque mechanism that was actually coming up with those decisions. Again, that's super important when we're thinking about this for fairness. If we can't point to what went wrong or what went right, then we really can't say that these algorithms are fair. Then if we look at the role of individual units, they are complete, right? Because they're actually showing the particular part of the input that was important to a set of neurons or vectors, but they're not interpretable. I have no idea what this part of the image means to the underlying process. So it's very hard for me to be able to present something like this into a screen, into something like a court of law. And then finally, the attention-based mechanisms, they are interpretable, but they're not complete. Remember that the sort of textual justification that comes along with these attention-based mechanisms are trained on a completely different process. So why does this matter? Well, interpretability matters for a multitude of different things. It's very important for the General Data Protection Regulation in the EU or GDPR. People have a right to explanation. They should know what these algorithms are doing. But it's extremely important for thinking about liability for decision-making. We have had self-driving cars that have already gotten into accidents and they have no way to recount what happened and why. And this is affecting human lives. It's affecting it in different types of ways. And we have no way to interpret what these opaque machines are doing. Why does this matter for completeness? I think this is very important, especially for this audience. You could be explaining the wrong thing. So many, many moons ago, when I was working at Xerox PARC, I was working on healthcare fraud detection. So I was looking at healthcare claims and trying to figure out when a claim was fraudulent or not. A common behavior that we would see is we would see something like a double billing amount. So for a single procedure, the person would get billed twice, right? So that means that the healthcare insurance company is making twice the profit. And we usually see these types of claims and we would say, oh yeah, we got him, we got the bad guy. But what really happened in a lot of these cases was that this wasn't fraudulent at all. This was something like a procedure on twins and it had to be billed twice. And what's important there is that we were actually explaining the wrong thing. We were trying to explain the fact that the billing amount was super important and it was outside of the normal range, which is what a lot of us do in types of machine learning. However, once we have an explanation, we start to realize that actually this isn't doing so bad after all. Another really important thing is that we can be making decisions for the wrong reasons. Again, especially important to thinking about this type of audience. It was shown by Claudia Parrish at Women in Data Science, this issue of data leakage. So there was a big contest on detecting breast cancer from images. And they were training their different classifiers. And what they found was that one of the classifiers was super accurate. So it was getting like 99% accuracy. For anybody who works in machine learning, when you get a classifier that gets 99% accuracy, you know that something is wrong. And so what they did is they tried to explain what this classifier was doing. And what they found was that the classifier wasn't learning the wrong thing. What they found was that the patient ID was very indicative. What that means is that the machine learning classifier was not learning whether it was breast cancer or not from the image. What it was learning was whether it was breast cancer or not based on where the image was taken. So, for example, at a breast cancer hospital, people are more likely to have breast cancer than at a normal hospital in, a normal city. So it was actually memorizing the patient ID, which was indicative of which hospital it was at. So again, it was getting very high accuracy, but it wasn't actually learning what it should. And so this is why it's very important, especially for thinking about things like fairness. So let's talk a little bit about what's actually being explained in these systems. So again, if we go back to our sort of on taxonomy of explainability, we have our visual cues, role of individual units, and attention-based mechanisms. The visual cues are really just explaining processing. They are taking a very complex deep neural net, they're simplifying it down to something like a saliency map, or even in some cases, a decision tree or a linear model, and they're explaining another type of processing, but they're not explaining the underlying mechanism, okay? Now that's very, very important. We should always use interpretable mechanisms when we can, but again, this is not going to be useful when we're thinking about things like accountability and fairness. The role of individual units is really just explaining a certain part of the representation and showing that with respect to the input that you have. And then the attention-based mechanisms are really just there to produce an explanation. We don't know if it's a good explanation, but it's providing some type of explanation that may be useful for some people. And in fact, we can use this taxonomy to characterize many different parts of the machine learning pipeline, especially for explainability. So processing methods are like proxy methods, decision trees, saliency mapping. Representation is explaining the different parts of the deep neural networks. And then explanation producing systems can be anything from disentangled representations to attention-based mechanisms. I'm going to give some examples of each to sort of show you what that looks like, and then I'll talk about the implications to complex systems. So methods that produce processing can be anything like deep red. This is a rule extraction technique. There have been many other techniques associated with this, or this can be things like LIME, which are basically these are approximate models that can explain any type of classifier. One of the big things to note here is that these systems are great, but again, they're not actually explaining the underlying processes. They're just creating a simpler process and using that as an explanation. So we've seen before what these sorts of saliency maps look like. They're basically highlighting the different parts of the image. And then deep red is actually creating a rule list or a decision tree of what actually happened. Here's the problem with that. The problem with creating these really complicated decision trees is that people actually aren't able to interpret decision trees that are very large. And these decision trees end up being very large. So we might find these indicative features, but they're actually not useful for the people who are looking at them. So now we're going to look at the sort of representation aspect. So this can be anything from network dissection, PCAV. There have also been work on this for things like CNNs. And again, what these look like are basically ways that you either highlight the individual part of the input that was important, or you create higher level concepts that can help you explain what you already know. Okay, so for example, in TCAV, if you have something like a fire engine, right, it finds that the concept of red is very important. And for something like a cab, it finds that the concept of yellow is very important. Again, this is really great, and this really helps us to diagnose these types of systems. But when we're thinking about this for fairness and accountability, there's no type of counterfactual type of reasoning. We don't know if the fire engine was green instead, we don't know how that would affect different things around us. So Moving on with the taxonomy, the methods that produce explanations, those could be anything from multimodal explanations to visual question answering, and even some GAN approaches as well. We saw some examples on the previous slides, but what do these actually look like? So largely what these will do is they will use some type of approximate method to highlight the part of the region that's important, and then use some other type of natural language generation tool. This work was done before the age of GPT-3, so largely these were other types of large language models, something like an LSTM. This is also related to a bunch of the work that I do in my lab, which is in modeling this as a complex system. So actually using the explanations as an internal debugging language, which I'll get to in the last 10 minutes or so. I wanted to just sort of highlight what the issues are here, especially thinking about this for fairness and accountability. The problem is that a lot of what we're doing here is we're just approximating really complex things. But the problem is that these insights actually matter. When we try and explain ourselves, we're actually explaining some type of black box, right? There are many different connections in our brain that are going off when we're trying to form a natural language sentence or when we're thinking to ourselves. But those connections are very important, and those are actually what make us intelligent. And I argue that we really need to think about those, especially when we're using these in lieu of human decision making. This is also very important for complex systems. We can't just approximate, a car with a computer vision system. There are many insides and mechanical parts that are super important to making sure these things work well. And of course, thinking about that for medical diagnosis, when these have repercussions to people's lives, we can't just memorize where the image came from to be able to detect breast cancer. We actually need to get to the root of the problem to show that this works. And again, this is a huge problem as we create neural networks that are getting bigger and bigger and bigger, and they are still not explainable. We have no way to sort of assure people that these are making decisions in our best interest. So with that, how do we evaluate it? So how do we say whether this is a good explanation? And again, what does this mean for people thinking about this in the fairness and accountability literature? Well, we already know that things like visual cues are interpretable. So how we actually need to evaluate this is with respect to completeness to the model. If we know that something is interpretable, then we have to say how well it actually expresses the underlying model's processing, whether we can trust it or not. For thinking about the role of individual units, then we have to say, are those units or those specific parts of the neural network, are they important to other tasks as well? Do we find that these layers are really important for other types of decision making? And then finally, for thinking about things like attention-based mechanisms, then we really need to use something like human evaluation. So these are what I argue we should really be thinking about. And the big problem here is that actually human evaluation is what's used for most explainability methods. But again, if we're going to use these types of deep neural networks, these types of machine learning systems in lieu of human reasoning, they really need to be evaluated on sort of a multifaceted scale. Which brings us to, the bigger challenges in explainability. So the biggest one is that we just don't really have good standards and metrics for explanations. Again, especially thinking about things like fairness. No one really knows, how do we actually evaluate these? How do we say, oh, this is a good explanation versus this is a bad explanation? We have no theoretical tenets for that. The current metrics that we have for evaluation are really fuzzy. And in fact, these types of user studies and user-based evaluations are not always appropriate, especially when we're thinking about complex systems. And then what we really need is we really need better benchmarks for safety critical and mission critical tasks, especially again, as these are being used in lieu of human decision making. And so what I'm going to talk about in the last part here is actually a way that we can generate these better benchmarks that are inherently explainable and that can ensure fairness for safety critical and mission critical systems. So I'm going to talk about our danger framework for self-driving cars. So before I get there, I'm going to pivot a little bit to, in the last few minutes here, to just describe what is being done in self-driving cars. So the examples that I showed today were largely for any type of image processing system that's being classified by deep neural nets, but this is also largely being done on the camera data of a vehicle. So the camera unit of a vehicle gets some type of image. It is put through some type of deep neural network, like the Inception network at Google, and then it gets some type of label, for example, that this is a pedestrian. Okay, and most of the time, this works very well. So most of the time, this works with upwards of like 95% accuracy. The problem is that when it's wrong, we don't know why, right? The big problem here is that these neural networks are brittle. And we've seen this in the case of adversarial examples. So this is obviously a picture of a pig. Hopefully you all agree. with just a little bit of noise, so 0.005, of this noise image here, we actually get that the deep neural net now thinks that this is an airliner. So it's been fooled by what's called an adversarial example. So adding a little bit of noise that we can't see. So what's being shown there is that these neural networks are really, they're not learning anything extremely important. They're just memorizing different features. And this was a way to sort of fool it in terms of these low-level features. Again, what are the implications of this? The implications of this is when the same technology is put on a self-driving car that's affecting people's lives, that's making unfair decisions, they really need to be explainable. And I sort of showed that in the beginning with this stop sign example with where a few pieces of tape, all of a sudden it's classified as a 45-mile-per-hour sign. And so the big problem here is that when we're thinking about things like self-driving and other mission-critical, safety-critical applications, these mistakes have consequences. They have to be explainable. And the big problem here is that we don't have the right benchmarks, we don't have the best data, and we don't have the right metrics for saying when are these safety critical, when are these accountable, and when are they fair. And so what we've been doing in the research of my lab is we've really been inspired by real world adversarial examples, and we are trying to create these types of data sets for other benchmarks for not just my lab, but also across the country. So this is an example of a realistic adversarial example that somebody actually saw, and then they put it through a deep neural network. So this is a truck, and it's correctly been classified as a truck, and I apologize, it's a small image sampled up, so it's a little hard to see. And the truck is carrying traffic lights, right? So if we saw this driving down the freeway, we would just say, oh, well, whatever, truck carrying traffic lights, keep on going with your day. But a self-driving car sees this, it detects the traffic light, it has no internal reasoning, no common sense, and it says, oh my gosh, that's something that I have to stop for. Again, there's nothing inherently wrong with this image, right? But it's an example of a real world adversarial example that can fool some type of computer vision system on a car. And we really want it to sort of learn from experience. So this is one example of what we would really want to see in a training data set. How do we generate data sets that contain all of these types of instances? And this is part of a much bigger problem, which is that we really lack data and challenges for autonomous vehicles and other safety critical, mission critical systems. The big problem is that the existing challenges are targeted at optimizing a mission or trajectory and not safety. It's very hard to define what does it mean to be safe. Many people hear, what does it mean to be fair? These are hard things to define. They mean different things in different contexts. The other thing is that the data is hand curated. So it's all perfectly curated. It's been cleaned. All the bounding boxes are tight. Everything's perfectly labeled. So we don't have any types of errors to learn from. And the other thing is thinking about this is that the failure data is just not available. It is unethical to get. I can't just tell my self-driving car or even, people in their cars, record your car data and then get in an accident and send it to me. That is unethical. We can't just drive ourselves into bad situations, right? However, we also want the data to be realistic, and that's very difficult in simulation. So our approach has been basically, can we apply this? So can we use content generation to have an anticipatory thinking layer for error detection? What do I mean by an anticipatory thinking layer for error detection? I mean, can we learn from instances like this, right? To say, oh, this is obviously a dangerous situation. No one should be swerving through, the highway like that. And can we use that to automatically augment the existing data sets that we have to basically take that type of behavior and then put that into an existing data set? So we have a self-driving car data set. It has a bunch of cars moving around. We take the cars out, come back in, making all these types of anomalous actions. And the key point with doing that is that this actually just becomes a sort of geometry problem. And the nice thing is that the trajectories that we add in, not only are they dangerous, we also know why they're dangerous because we generated them. So they're explainable by design. So we know that someone making a sine wave on the freeway is clearly that is not something that they should do. And we know why it's not something that they should do. So I know I'm running out of time, so I just wanted to sort of talk about why these have implications besides just thinking about the image world. So in summary, I started with a brief intro and motivating the problem that these systems are imperfect. I talked specifically about that in the self-driving car literature. I talked about the need for explanations. I talked about what's actually being explained and how that doesn't necessarily align with what we want to do in accountability and in fairness. I talked a little bit about how we evaluate it and how we can think about that moving forward, and then how we can actually use that to explain critical systems to create better types of data sets that are more representative of the things that we would see in real life. So I will end my talk there, and I'm happy to take questions and discussion.
Thank you so much. So you can put your questions either in the chat or in the Q&A, or if you'd like to, because I think we're a small enough group, please feel free to unmute yourself after raising your hand, and we'll call on you and you can ask your question directly. Elizabeth, go ahead.
Thanks a lot. This was very interesting, and I'm also interested in explainability. And my question is, you had these two parts like interpretability and completeness. And completeness you defined as describes operation in an accurate way. And accurate, if I understand you correctly, means in a correct way in this definition. But completeness, couldn't this also be like a complete explanation in the sense of a comprehensive explanation, isn't it? And I just want to ask around this, and where would the comprehensiveness come in, or does this matter, or does this not matter? Because of course we can always ask, okay, is this enough explanation? Don't we need more? Do we need more? How do you explain this? We can always try to go a step back. And when is an explanation an explanation? That's just, if you could fill some of these things in.
Oh, absolutely. First of all, Elizabeth, great question, very open question and explainability. So I will try and do it justice. So when we talk about completeness, what we really want to have is an explanation that actually points to the underlying mechanism and where it made those decisions. So actually saying the reason that this is a dog is because neurons 5, 6, and 7, who are related to the dog features, thought it was a dog. We currently don't have the technologies to do that right now. There are some, network dissection techniques that exist, and we're starting to get closer to it, but that's also very related to what you're saying about comprehensiveness. The big problem is that a lot of people who want an explanation just want a surface level explanation. They want something that says, oh, like if I'm talking to you and I say, oh, well, I'm fine today, that's usually okay. And people would accept that as an accurate explanation, but the full explanation would be so long that no one would actually want to listen to it. So there's really a trade-off between how expressive your explanation is, how much it actually represents the underlying processing, and also how appropriate it is to the user that you're delivering that explanation with. And a lot of people are thinking about ways that you sort of incorporate those things together, but there's not one, a one-fits-all type of solution.
Thank you. We have one that came into Q&A. Sorry about that. So which of the 3 methods of explainability that were mentioned is currently widely adopted? And based on their advantages and disadvantages, should we use them simultaneously?
I am a huge proponent that we should use them simultaneously. I think there are many different explanations for different types of people, for different types of applications. I think when you're trying to explain things, you should use as many explanation mechanisms as you can, and then see which ones align with your domain knowledge and for the user or mechanism that you are showing that explanation to. The first part of the question, which one is the most readily used, and it is mostly the visual cues. And the reason it's mostly the visual cues is because most of the deep neural networks and opaque mechanisms that we want to explain are for visual systems, and that is an interpretable way to see where these visual systems are explaining. But again, the issue is for you guys as well, like a lot of what we do in the fairness literature is looking at tabular data, or it's looking at, we want to look at counterfactuals, and saliency maps cannot do that type of reasoning. So I would argue that we definitely want as many explanations as we can. We need better ways to debate between those explanations. I do have some work on that, although I didn't get to it today. But yeah, the most readily used one are these visual cues.
Thank you. Robert Ellis, would you like to ask your question?
Hi, my sound coming through okay? Okay.
Yes.
I guess I have 2 questions, a little bit related. The first is, what if we'd like to help undergraduates studying machine learning start to learn explainability, but they're not ready for neural nets? Maybe they need to start learning it in the context of simpler models. And second, I guess, is a little bit related. I was wondering if anyone has worked on explainability for things like sentencing guideline software in the judicial system, more so than just kind of reverse. There was a work that was like reverse engineering some kind of linear regression for Compass, but I was wondering in general if you knew more about that.
Two great questions. So I'm very interested in the first, which is how do we use explanations for education, especially for teaching people, especially for teaching undergraduates. I teach the Introduction to AI class, and I'm a big proponent. I mean, linear models and decision trees are great, and they're explainable by design, and they are also machine learning and AI tools. So I'm a big proponent of using those and teaching people how to use those to actually diagnose their systems. I'm really interested in ways that we can represent multiple types of machine learning and AI tools by these inherently interpretable methods. So I think that's a great place to start. For your second question, which I think was about using explanations to reverse engineer some of these practices, I've seen a little bit of work in that. I know that the White House put out some guidelines for explainability, and that was one of the threats, although they talked about it at a very high level. I don't know if people have done that in a technical sense, but I know a lot of people have used this in security for reverse engineering. I wouldn't be surprised if they're taking similar techniques and then applying them to these problems as well.
Thank you. Daniel Schiff?
Yeah, thanks so much for this, Leilani, really valuable work. Since you're digging into this sort of broader landscape, I was hoping I could pick your brain a midway about this, and some previous people anticipated some of my questions. So thinking about tabular data, audiovisual data, text data, I guess what's your sense broadly about what's the most promising right now? Which areas do you feel like are reasonably solved? Like, is it decision trees and OLS? So what's promising, what's solved, and what's maybe stagnant or isn't a way that we think we may never solve this kind of thing?
Oh, wow. What a great question. I mean, I'm a big proponent of, Cynthia Zurden's work in decision trees. I think that they're like, if you want a gold standard of an explainable method, it is a decision tree. Now, again, it's not going to be complete if you use it for something like a deep neural network, but they're interpretable by design, they're explainable by design, and they work pretty well. And there's a whole lot of literature about how accurate they are, which is very important. Now, decision trees also have huge issues, which is that they're extremely unstable, right? You run a decision tree algorithm especially on tabular data. You do that several times, you're going to get a different decision tree anytime. I think a huge ripe area of research too is how do you create fair decision trees, right? Largely, it takes these decision trees many iterations to sort of create, their structure. But if you identify a feature that's clearly unfair or it's biased, how do you take that out but retain the type of accuracy? Because largely we don't know that that's the feature we don't want to focus on until we see it. So I would say, if people are getting started in this field and want to look at something, I would definitely look at this sort of decision tree literature. But again, when we're thinking about real world problems, they're actually not as applicable. And there are a bunch of, there are huge amounts of open problems in this field. I think actually the biggest one is related to the first question, which is that it's not a well-defined field. And I actually think people who are working in the interdisciplinary sciences have a very, a key role in saying, when I'm working on explainability for, bail, this is what I mean. Because, an explanation means different things to different people, and it means different things in different applications. So I think that's the key question.
Thanks so much.
Mm-hmm.
All right. So if you have a question, we will please hold it. Oh, okay. So we can have one more question. Please go ahead.
Sorry about that. So the great presentation. My question is about, is it fairness in ML considered at all when people decide, to use AI, for example, in police department or somebody said the justice, system and other places?
I mean, great. Also great question. I think it's very related to Daniel's point as well. I think that a lot of the people who are working on fairness in AI, and I should say, I don't necessarily work exactly in that field, but I do work in sort of more responsible data science, explainability. I think it's always an afterthought. Like somebody creates a model and then they say, okay, now I'm going to try and explain it. And now I'm going to see if it's fair. And I think that we have to start thinking about these things before we start even training our model. Because, for example, with the Amazon recruiting tool being so unfair, like, I don't know if there were a couple women at the table, I'm sure they would have said, oh, training on your previous, intern resumes that are 99% male, that's not going to be very fair. So I think that there are people who definitely think about that, especially in fairness in machine learning and fairness in AI. But I think a lot of the typical AI and machine learning developer, it's an afterthought. And at that point, it's a little too late. And it's also really hard to augment the algorithm. We have to do an entirely retraining process. So, and that's just my experience. I'm sure other people have other ideas, but that's why I also think it's so important to talk about these issues in every computer science class that we have. Because these are the people who are going to be, working at these top tech companies, and maybe there's somebody who raises their hand and says, hey, actually, I don't think that this is the right thing to do. But yeah, I mean, it depends on the institution and the area, but I would say largely, unfortunately, it's an afterthought.
So if I understood you correctly, I think it's really hard to measure whether, a machine learning or a program, is fair or not. And we have to see, what happens because of all those mysterious things that happen in between, from the input to the output part. So is there any way that we can address this, to, as we said, evaluate these programs beforehand?
Yeah, I mean, I think a big tool, I know I'm running out of time, so I'll be very quick, but I think a big tool that we can start to use, I know they're a little bit scary, but some of these generative AI tools to generate things that are possibly out of sample, to use that for testing would be really great. I think some people are starting to use that. But I think, a lot of what we see with fairness, it's the same thing with explainability. Like, you don't know it unless you see it, right? So you train a classifier and then you detect afterwards that it's really unfair. Like, I think we have to think about better, like, stress testing mechanisms for the early stages to detect these things before we deploy them in these large scale environments.
Thank you.
All right. Thank you so much, Dr. Gilpin, for your presentation. It was very informative and insightful. Next, we have Dr. Lindsay Weinberg. Dr. Weinberg is a clinical assistant professor in the Honors College at Purdue University and the director of the Tech Justice Lab. Her research and teaching are the intersection of science and technology studies, media studies, and feminist studies with an emphasis on the social and ethical impacts of digital technology. She is interested in the constitutive role that history and unequal power relations play in shaping the design, application, and reception of technological innovations. Her work has appeared in several esteemed journals. Her book project, tentatively titled Smart Campus, Education and Surveillance in the Age of Austerity, examines the proliferation of digital tools for higher education governance and their impacts on marginalized people within and beyond the university's walls. She has been the recipient of internal and external grants to support research, seminars, and workshops concerning the justice-related implications of digital technology, including from the National Science Foundation, the Indiana Humanities, and the Susan Bulkley Butler Center for Leadership Excellence. Dr. Weinberg will talk about how dominant trends in AI fairness research entrenching rather than remedying issues of bias and discrimination. In a specific, Dr. Weinberg will talk about the predatory inclusion of marginalized groups into AI systems, the absence of participatory design and democratic deliberation in machine learning fairness considerations, and the influence of private tech industry funding on AI fairness research. We are really grateful to have her today. Dr. Weinberg, the floor is yours. Thanks.
Thank you so much, Layla. Let me go ahead and get my presentation up for us. Okay. Okay, hopefully this is visible to you all. Okay, so thank you so much. I'm really delighted and honored to be here today. I'm joining you all from Purdue University, where I currently research and teach about the social and ethical implications of digital tools, but particularly predictive analytics and AI in the context of both higher education and the criminal legal system. So I'm actually going to talk quite a bit today about Compass, as well as a few other examples to kind of think about the critique of machine learning fairness discourse that I'd like to offer. I just want to start by thanking Leila again for inviting me, as well as the Illinois Tech Ethics Center. And I'm just really excited and privileged to be part of the conversation today. So for this presentation, I'm going to be drawing from my experiences working on a grant that was funded by the National Science Foundation's Program on Fairness in Artificial Intelligence in collaboration with Amazon. More specifically, I'm going to talk about how dominant trends in machine learning fairness research are entrenching rather than remedying issues of bias and discrimination. Together, we're going to look at some examples of the predatory inclusion of marginalized people into AI systems, the absence of participatory design and democratic deliberation over machine learning fairness considerations. And we're also going to look at the influence of private tech industry funding on machine learning fairness research as well. So the project I worked on was spearheaded by Dr. Chris Clifton, who's our head of computer science at Purdue. But I also worked in collaboration with several other researchers in computer science, human-computer interaction, and philosophy, not only at Purdue, but the University of Chicago and the University of Texas at Dallas. So when I was brought onto the team, I was really asked to kind of provide a feminist science and technology studies perspective on what it might mean to identify, measure, and mitigate fairness issues in artificial intelligence. And in case there are those in the audience who might not be familiar with what kind of feminist science and technology scholarship is, many feminist STS scholars are interested in how technologies reproduce relations of domination and subordination. We also are interested in how claims about technology's neutrality or objectivity can conceal the ways that tech participates in many historically long-standing forms of injustice. Many of us are also interested in imagining ways that we might appropriate or modify or contest or embrace liberatory forms of technology in order to bring about a more just future. And it's really in this spirit that I've come to kind of share some things with you folks. Before I kind of talk more about my work on this specific project, I want to just take a moment to note some of the epistemological and normative assumptions that were baked into the NSF program that ultimately funded our group's research. So I'd just like to kind of direct your attention here to the bolded portions of the slide, because this is kind of taken directly from the grant's call for proposals. And I want to kind of show that there's kind of a very explicit goal baked into the NSF program, and that's about kind of funding computational research in particular that will promote the acceptance of AI systems, and AI's capacities for social good are largely being presupposed a priori in this grant call as well. So as a feminist STS researcher, I see these assumptions as a feature of the ways that power relations shape knowledge claims, including the research that traditionally gets funded and given access to do this work, who generally gets to conduct this research as well. So my participation on this team was really conditional upon having autonomy over my research methodology and findings, which are not kind of traditional computer science research. But there was also a lot of work we did at the grant proposal stage to kind of frame my efforts as in keeping with this particular call for proposals. And so what I've learned kind of from doing this project has really gotten some kind of firsthand insight into both the possibilities and the risks of academic research partnerships that are done kind of with funding from private tech industry. And on the one hand, I think they make possible these really incredible transdisciplinary collaborations that have significant financial expenditures. But on the other, they create great potential for industry ethics washing and the curtailment of academic freedom as well. And many of us know in the case of Amazon, I would argue that Amazon is a company that's anti-Black all the way down. It actively forms partnerships with police departments. It drives small Black businesses out of the market. It retaliates against Black warehouse workers who were calling attention to unsafe working conditions in the COVID-19 pandemic. They have a logistics empire that disproportionately harms Black communities through pollution as well. So what does it mean to kind of take funding from a company in the name of fairness, and yet that kind of traffics in all kinds of systemic forms of unfairness as well as a fundamental part of its business model? More broadly, I think there's a trend in academic AI ethics research wherein industry funding shapes the framing and priorities of the conversation. It could shift discussions kind of towards industry self-regulation, and that could look like voluntary ethical principles or responsible practices or technical adjustments rather than kind of robust legally enforceable restrictions. Furthermore, modern AI often requires a significant amount of computing resources, and many of those are kind of costly and oftentimes provided by big cloud services, typically operated by big tech. And as Meredith Whittaker describes in her article, The Steep Costs of Capture, this doesn't necessarily mean that, quote, researchers within these domains are compromised. Neither does it mean that there aren't research directions that can elude such dependencies. But it does mean, however, that the question and incentives that animate the field are not always individual researchers to decide. So this is something that I think we want to think very carefully about what does it mean for industry to fund AI fairness research and how that could condition and constrain the ways that we learn to even talk about notions of fairness. So in my work on this project, I was really interested to understand the kind of values, the goals, and the assumptions that are shaping how fairness is being conceptualized within computer science research. How do we define it? How do we measure it? And what might be in need of problematizing? And so while there have been many efforts as of late to kind of propose these quantitative metrics for measuring the fairness of a given machine learning tool, these measures often rely on a suite of unstated assumptions about fairness in society. And it's those assumptions that are shaping how machine learning tools are being both conceptualized and tested. So just to kind of give a concrete example to help us think through this, we can look at the ways that a wealth of computer science research on fairness in machine learning takes up the example of COMPAS. COMPAS is a tool that uses machine learning to generate risk scores, and those risk scores are then used to inform judges when making decisions about, whether to offer a given defendant bail or how to sentence them. And according to proponents of the tool, these risk scores will help judges to be more impartial than if they were to make these decisions on their own. But when the nonprofit news organization ProPublica released a report arguing that COMPAS was biased against people of color, there was then a flurry of machine learning fairness research that ensued to kind of work to test ProPublica's results. Ultimately, 4 independent groups of researchers found that it's impossible for COMPAS to measure and treat Black and white defendants fairly. These studies determined that the risk score could be either equally predictive or equally wrong for both races, but it couldn't satisfy both of these fairness constraints simultaneously. The reason for this outcome is because of structural racism that's embedded in the training data. It reflects policing practices and criminal court proceedings that are themselves biased against people of color. And many machine learning fairness researchers have since been working on developing computational improvements for COMPAS in order to improve outcomes for Black defendants. And this includes fairness criteria that draw from Black feminist traditions, such as the idea of intersectionality and the need for fairness criteria that account for the intersections of race and gender is just kind of one example. However, what my work is trying to stress is that the unfairness of COMPAS extends beyond issues of data bias. The tool's very existence is biased towards incarceration. Only incarceration's relationship to recidivism has been measured in a manner that's kind of conducive to machine learning. And this is in contrast to many non-punitive alternatives that abolitionists have been arguing for decades, and that includes the ending of cash bail and pretrial detention altogether. So thus, the ways problems are being framed within machine learning fairness research creates a limited political horizon concerning what's possible to transform about the unfairness of the US legal system. And so this fixation on notions of measurable mathematical ideas of fairness more broadly, no matter how intersectional, can obscure the root causes of unfairness in society. There are a range of other issues with hegemonic approaches to improving the fairness of machine learning tools. So for instance, images of students, immigrants, abused children, and people who've had mugshots taken have all been used without their consent to improve facial recognition technology's accuracy for marginalized groups in the name of fairness. Yet no amount of increased accuracy in FRT is going to change the fact that low-income communities of color are over-policed in the US. So more accurate facial recognition technology for some of these groups may in fact increase these groups' vulnerability to unfair forms of kind of encounters with police officers. While this sort of machine learning fairness research that seeks to kind of tweak the fairness of fundamentally unjust systems is incredibly damaging, this trend is perhaps unsurprising. There is pervasive racial, gender, and economic justice in terms of who's admitted to the AI field, who gets mentored, who gets turned to for collaboration, who gets hired in academia, and who gets given adequate financial and institutional support. So it was with kind of this framing in mind that I approached this project. And what I did was I kind of evaluated 50 critiques of fairness in machine learning from the humanities and social sciences in order to help inform how my team would then approach the computational research portion of the project. And then within the existing scholarship, I tried to kind of synthesize and distill 9 major themes of critique. So the first was how fairness in machine learning fairness research gets defined, often as a kind of procedural or statistical goal, rather than this kind of complex and highly fraught philosophical concept. The second one was how problems for machine learning tools to address get formulated, such that the problem is largely defined by data scientists or industry rather than community needs. I looked at the impact of abstraction on how machine learning tools function and kind of abstraction's propensity to lead to technological solutionism. I looked at how racial classification operates within machine learning fairness research, such that race is kind of treated as this neutral marker of identity rather than a social and political system of classification. I looked at the use of machine learning fairness measures to avoid regulation and engage in ethics washing by kind of maintaining the power to decide what's fair in the hands of technologists and industry stakeholders. I looked at the absence of participatory design and democratic deliberation in machine learning fairness considerations, which sidelines and silences impacted and marginalized communities. I looked at data collection practices that entrench bias, that are non-consensual, that lack transparency. 8 was the predatory inclusion of marginalized groups into AI systems, such as the kind of non-consensual use of marginalized people's images in order to kind of quote unquote improve the fairness of facial recognition. And finally, 9 was a lack of engagement with machine learning's kind of long-term social and ethical outcomes. For the remainder of this talk, I'm going to focus on numbers 1, 3, 6, and 8, but I'd be more than happy to kind of expand on any of these points during the kind of discussion portion for today. So let's start with the predatory inclusion of marginalized groups into AI systems. And just to give you kind of a working definition of what I mean by predatory inclusion, I mean cases where data and or labor from marginalized people is taken in order to improve the so-called fairness of a given machine learning tool. I spoke a bit about this in the context of facial recognition technology broadly, but I'd like to offer a few more concrete examples to think with, and I'm going to draw from higher education in particular. So between 2012 and 2014, researchers at Duke University, Stanford University, and the University of Colorado at Colorado Springs captured images of students traveling between classes and visiting on-campus cafes. These images were taken to help improve AI's capacity to recognize people in motion within a natural environment. At UCCS, in a study approved by the institution's review board, long-range surveillance images of over 1,700 people were collected in February 2012 to September 2013 without students' knowledge or consent, which helped to produce a data set with the kind of desired real-world conditions for defense and intelligence agencies. In the case of Duke University, the lead researcher made significant changes to the approved project that went unreported to the IRB, including expanding the project's scope from the indoors to the outdoors and giving data access not only to researchers upon request, but kind of to anyone as a publicly available data set. When researchers on these studies were pressed about kind of the ethical implications of taking student images without their knowledge and to improve technologies that are used to kind of discipline and control populations at home and abroad, the researchers stressed that the inclusion of diverse student images in a natural environment will ultimately help reduce false positive identifications. So here, researchers were kind of leveraging critiques of FRT bias to justify the predatory inclusion of student images. And I consider this form of inclusion predatory because it was done without students' knowledge and consent, and it was done to improve technologies for state surveillance and repression. Another example we might think of in higher ed is, of course, ChatGPT. So on the one hand, you know, there are well-founded critiques of the ways marginalized people are excluded from the AI development process, wherein design and deployment are kind of kept firmly in the hands of technologists. But in the case of ChatGPT, you know, workers in Kenya were involved in the design process, but they were paid less than $2 an hour in order to kind of help build a content filter system. The headlines about these exploitative labor conditions, which perpetuate long-standing forms of colonial power dynamics between the global North and global South, kind of came and went as academia kind of became fixated on issues of academic integrity. You know, would our students use ChatGPT to cheat? And yet these workers in Kenya were arguably doing the work of AI fairness. They were helping to reduce discrimination and other harmful outputs. This labor is undercompensated. It's rendered invisible to many users in the global North as well. Another example we might think of outside of higher ed is Google contractors targeting unhoused people with darker skin tones in order to improve the fairness of Pixel 4's biometric technology. Unhoused people were reportedly offered a $5 gift card in exchange for an image of their face. While an example like this might seem particularly predatory or egregious, dominant trends in machine learning fairness research rarely engage with robust ethical forms of participatory design. And yet researchers include images and labor from marginalized people under the auspices of making these technologies more inclusive for all. Perhaps most commonly outside of web scraping, people from marginalized groups are invited to provide input on the fairness of a given AI outcome using services like Amazon's Mechanical Turk, but where they are otherwise not engaged in the AI tool's development, nor empowered to effect any changes over its design or implementation. This lack of democratic deliberation about whether a given AI tool should be used at all, as well as what fairness judgments should be prioritized about it, is another issue that's perpetuated by common trends in machine learning fairness research. In many cases, machine learning is being integrated into politically and institutionally significant ways without meaningful debate or substantial opportunities for contestation as well. Either the exclusion or predatory inclusion of people who are multiply burdened by systems of power and machine learning fairness research has helped perpetuate the flawed notion that machine learning is marred only by biased data. You know, if only we were able to operationalize the right procedural or statistical guideline, then we'd have a fair ML tool. This understanding of bias as computational rather than a social problem obscures root causes of unfairness in society, and it perpetuates the notion that technologies can and should ultimately adjudicate the fairness of a given tool. Within hegemonic machine learning fairness research approaches, quantifiable fairness metrics are prioritized over a range of other value considerations that could include downstream effects, as well as possible non-technical solutions in a given domain. So again, if we return to the example of COMPAS, the tool's prioritization of recidivism rates could have the long-term consequence of leading a judge to place a greater emphasis on incarceration as kind of the goal of sentencing, which could then lead to subsequent policy and legal changes in a context that is already favoring of mass incarceration as a so-called solution to structural inequality. It's also the case, as argued by Shira Mitchell and her colleagues, that a range of utilitarian assumptions are generally built into predictive models, including the assumption that outcomes are not affected by the decisions of others, that social welfare is a sum of individual utilities, and that individuals can be considered symmetrically. So for example, that the harm of denying a loan to someone who could repay it is going to be equal across people, when in practice this is hardly the case. This issue connects to concerns scholars have raised about abstraction in machine learning fairness research, wherein the social context of these tools is generated within and applied to are largely removed from view. Formal approaches to machine learning fairness often fail to account for potential harms, such as biased practitioner use, or how a given AI tool is going to interact with and potentially change pre-existing behaviors and norms, as well as alter existing struggles for power to decide how rights, resources, or opportunities should be distributed in society. This propensity for abstraction is kind of baked into the fabric of computer science education for many students as well. So James Malazita and Corinne Rezatar have shown that within computer science education, technical competency is often split from the social, political, and ideological world. This split is doubly impactful for marginalized students who then have to embody knowledge practices and epistemological frameworks that counter their lived experiences. According to the authors, abstraction in computer science intentionally limits knowledge of the broader system coding practices and are situated within for the purposes of efficiency and kind of achieving predetermined specified goals, which problematically constrains what counts as relevant points of intervention, oftentimes alienating marginalized students from the field in the process. Unfortunately, calls to democratize AI have already been co-opted by industry forces as well. Rather than democratizing questions of whether a given tool should be built at all, these efforts to more widely disseminate the infrastructures for producing and advancing AI throughout academia, including through the creation and distribution of large data sets through scraping the web and other non-consensual means, seem to be the most popularized. As Whitaker explains, quote, these proposals to democratize access to AI research infrastructure amount to calls to subsidize tech giants further by licensing familiar infrastructure from these firms in ways that allow them to continue to define the terms and conditions of AI and AI research. Ultimately, my work on this grant led me to conclude that we need a wholesale rethinking of what fairness in machine learning is by centering anti-oppressive approaches. By anti-oppressive approaches, I mean approaches that are committed to undoing the unjust distributions of social, political, and economic power shaping the AI field. So just to give you some kind of concrete examples of what this could look like, it could look like participatory design that involves consent, compensation, opt-out options, and long-term partnerships with impacted communities. It could look like diversifying who generally gets to conduct this research and weigh in on its consequences. It could look like bridging divides between different epistemic communities so that data scientists are in conversation with the domain expertise of scholars from the humanities and social sciences, but also recognizing lived experience as a valid form of knowledge that impacted communities can offer as well. And finally, aligning machine learning fairness research with historically long-standing struggles for just community relations. So for instance, if you're building a machine learning tool to help make mass incarceration in the US fairer, you haven't been listening to what marginalized people on the ground and in prisons have been arguing for decades, which is less cages and not more fairly distributed ones. We must always remember that sometimes the solution is not to build the tool at all. I think it's also worth complicating how much emphasis is put on reforms that can be technically operationalized at the expense of other types of changes we might want to see in order to achieve fairer relationships with and through technology. So for instance, how might machine learning practitioners take up active roles in the struggle for complementary social, political, and legal processes that ensure just outcomes for marginalized people? How might machine learning fairness research be developed in solidarity with community and industry movements for progressive technological reform, for the rights of tech workers, and for greater agency, self-determination, and democratic control for marginalized people over AI tools? If machine learning fairness research is really to be about the creation of a fairer world with technology, then this research will need to align itself with existing struggles for racial, gender, economic, and climate justice. And if such a research program seems antithetical to the priorities of computing, then this speaks to the urgency with which the field needs to be transformed. Fortunately, there are already many efforts underway to kind of shift the discourse and priorities of machine learning fairness research, led by Black women scholars and activists within and outside of computing. So here I'm thinking of Khadija Abdurrahman, Simone Brown, Ruha Benjamin, Abeba Burhani, Safiya Noble, Leah Maria Hampton, Timik Gebru, the Coalition for Critical Technology, the Our Data Bodies Project, and the Stop LAPD Spying Coalition, among many others. These are scholars and groups I would encourage folks to check out if you'd like to think more about kind of anti-oppressive approaches to fairness in machine learning in particular. So thank you all so much for your time and attention, and I'm excited for our discussion.
Great, thank you so much. I think we're going to start with two questions that were put in the Q&A, and then we'll move to people who've raised their hands. So the first question is, here's a current Chicago example of potentially predatory exposure, of personal data in Chicago. There are roughly 400,000 lead service lines or lead service lines through which tap water goes to Chicago households, roughly 80% of all water service lines. If the city released the data, companies such as Blue Conduit, who work with Flint, Michigan, could with much higher accuracy predict the likelihood of lead poisoning of residents and perhaps prompt more immediate action. Should the city release this data? This is a question from Robert Ellis.
Yeah, thank you so much. I mean, I'd be very curious to hear your perspective, Robert, but I think most importantly, if you're working with folks who are impacted, if they feel like the sharing of the data can be done in a way that feels liberatory and empowering, and is done with their consent and is done in such a way that it's going to be again, giving these folks agency over how the problem is going to be solved, then I don't, to me, necessarily see why it would be such a bad thing, right? I think that there's ways that the data sharing could be done with a lot of intentionality, but I really think that centers on, are the folks who are being the most significantly harmed really at having a lot of power and agency over the conversation and where we go once that data has kind of been analyzed. And I think oftentimes what ends up happening is there's these demands for transparency, there's demands for accountability, but the transparency doesn't always get coupled with accountability, and it can actually allow already empowered stakeholders to be able to kind of manipulate the narrative in such a way that they can kind of downplay responsibility. So I guess that's kind of my take, but I'd be curious to hear what you think.
Okay, the next question.
Sorry, I'm a little slow. Thank you for that. Most people don't know what the composition of their service line is. I guess that seems totally reasonable. Whoever's making the decisions at the city level would decide for 400,000 households, and getting 300,000 of those who don't know to be involved is a pretty high hill to climb.
Yeah, I think that's a good point. And yet I think we see that there's a precedent for this kind of work, right? It might not be every single person who's been impacted, but even if we look at models for class action lawsuits, or we look at other kinds of ways that people take more bottom-up grassroots approaches to building coalitions around issues that are affecting their communities, like I think it's possible to imagine bottom-up ways of organizing around some of these issues as well, and data being used as a tool to empower those communities.
Thank you. So the next question we got in the Q&A is, how can machine learning practitioners incorporate these critiques that were raised in this presentation into their work? And what are some best practices for doing so?
Yeah, I would encourage you to kind of read the piece that kind of a lot of the material I've shared with today is kind of pulled from. It's a piece I wrote called Rethinking Fairness that really tries to both systematize these critiques, but also kind of offer some ways forward. But I really think I tried to offer some kind of concrete next steps. One is, I think, again, just familiarizing yourself with the literature that's coming outside of computing that I think has been interested in questions of fairness and justice for a very long time. And I think immersing oneself in that scholarship and also partnering with scholars outside of computer science could be a really good way of building a more holistic and interdisciplinary understanding of a given domain. But again, I think also there needs to be an investment in participatory design. I think there's so much emphasis that's put on efficiency and what can be operationalized and what could be done as quickly as possible in order to solve these seemingly intractable problems. But I actually think we can end up doing a lot more harm than good. And that's why being able to kind of partner with communities and making sure that this particular tool is going to actually solve the underlying problem, I think is another really important next step. And again, I think there's ways that machine learning practitioners can get involved both through, but also outside of computing as a way of engaging with some of these issues. And I think we've seen examples of this, like we've seen mathematicians who've refused to partner with police officers on predictive policing software in the wake of the kind of racial justice protests after the murder of George Floyd. But there's other kind of forms of refusal where folks kind of realize that because of the sensitivity of this given domain, because of longstanding issues of injustice, that no matter how fair of a given tool you produce, you're not going to be able to be really meaningfully address the root cause of the problem, and therefore maybe that a non-technical solution is more appropriate. So being able to kind of reason one's way through that, I think it's really about interdisciplinarity, and it's really about partnering with and being in solidarity with the folks who've been doing this work on the ground and who are the most directly impacted by it as well.
Thank you. Daniel Shith, I think you had your hand up first.
All right, so good to see you here, Lindsay. Your talk resonated a ton. I think it's the best summary of these critiques I've seen, really useful clustering, so thanks for this. So tough question, but was hoping you have some thoughts. So even on some of the consensus ideas that our community has come out with, diversification, public participation, interdisciplinarity, right, these can be co-opted too, and I think they have been co-opted. On the other hand, I think that there's a growing awareness of, let's say, socio-technical issues, awareness, higher willingness. So even in a NIST RMF conversation or EU AI Act or an industry, people say, oh, I see this, I kind of care about this, what to do. And I think there's an under-tapped willingness. So sort of, you propose some of this, but kind of what's the strategy here if we stipulated that we find these critiques, very valid and we want to change course? Beyond awareness building, beyond interdisciplinary, or is it doing interdisciplinary or public participation better? Is it these sort of finding more independent solutions like, don't train my data and compensating data? Is it more of these? Or is it something like, use case bans and normalizing that through regulation? Or is it really political transformation and that we can't do this without a deep critique of the social and economic systems? Sorry for the tough question, but any thoughts?
No, I think it's a great question, and it's one that I have complicated feelings about, right? Because I think I don't think it has to be one thing, right? Like I think people have access to different kinds of levers. Firstly, right? Not all of us are equally well positioned to tap into all different types of solutions. So I think that's one thing that I'll say. I definitely think, from my perspective, right, like more solutions that are more community and coalition based tend to seem more effective at addressing structural issues broadly, right? I think that's really important. And I think some of the more individualized solutions that we've seen have not been successful, right? So privacy and privacy rights is kind of an example of this. There's a lot of folks who've tried to use privacy as a way to kind of put up some blockages and barriers to some of the kinds of data scraping that's happening online, but they've been really unsuccessful. And I think it's because it's such an individual-based, rights-based framework. You have to be able to like demonstrate harm in a particular kind of way. And I don't know that privacy is really the best tool to talk about, discrimination and talk about things that affect a wide variety of people who share some kind of maybe group characteristic, right? So I think it matters what frameworks we invoke, and it matters to what extent we can really leverage large-scale organizing in order to make those changes happen. And I also have a lot of mixed feelings about like, what does it mean to go into industry, right? Like I work with a lot of folks and I've done research that's been funded by industry, but the more distance I have from that project, the more concern I have that, on the one hand, right, we need the funding, right? And on the one hand, doing AI research requires a lot of those researchers. And yet I think there's a lot of risk. So I have complicated feelings about like to what extent, if any, we should be really partnering with industry on some of these questions, particularly because I think the economic critique is a really, really potent one. And I think industry and the military, right, have so many kind of shared interests that we're seeing the direction of AI research move in a really, really scary and terrifying way. So yeah, I don't have a good answer, I guess, because I'm filled with a lot of ambivalence, but I do think collective as opposed to individual seems to be achieving the most. And I also think it's important to maintain a politics of refusal. And I think that it seems like oftentimes it's kind of a tacit acceptance of, okay, we have to accept that AI is going to be part of our lives in this particular domain. And it's just a matter about finding the right tools to justify it or make it more transparent or make it more accountable. But I think sometimes the solution is to say no. And I think folks have actually been quite great at having some successes, particularly around facial recognition technology. There's a lot of city ordinances that have been passed all across the country that have said, hey, this is not something we want in our communities, right? So I think it is possible.
Really helpful insight. Thank you.
Hi, Nancy. Thank you very much for the presentation. I really enjoyed it. It was very illuminating. And my question is, has there been any accountability for especially the researchers? You mentioned that I'm sure they are not alone, for collecting data without the permission. And then also, do you think bringing civil lawsuits against local governments or national governments or states could at least encourage, introduce a little bit of accountability, for these predatory practices that these organizations, at different level are doing?
Yeah, great questions. Yeah, in terms of the accountability for the researchers, to my knowledge, not tremendously so. And I also think there's a danger to kind of a bad apples framing, right? Because many of these researchers are doing this type of research and they do have full permission of the IRB. So even in one of those studies, they went through the IRB process, they didn't make any modifications to the IRB, and they were given consent to take the student images because the students have no right to privacy walking between classes, right? So it's research that's oftentimes being conducted above board, actually, but then nonetheless is kind of perpetuating these harms. But nonetheless, I do think accountability is, of course, really, really important, but I think we need to resist the temptation to kind of bad apples frame our way out of these problems. It's an industry that's kind of predicated on many forms of mass aggregate data collection that are sanctioned by law, that are sanctioned by our institutions. And I'm actually that's something that I'm very interested in, right? Like, how do we normalize injustice and unfairness in a way that is sanctioned by how our society is structured? And to your other question, I do think law is a site of possibility here. I think there are also very compelling critiques about GDPR and the new EU AI Act and things like that I think we need to be sensitive to. But nonetheless, I do think it at least provides an infrastructure for agitation. It at least allows for some kind of democratic form of conversation and contestation that's possible. I don't think it's the only solution, but I do think legally enforceable restrictions seem to be the thing that the AI fairness discourse tends to skirt around quite often. It's much more about technical measures and industry self-regulation and voluntary ethical principles. And I think there's a reason for that. And I think that tells us that it might be a generative site. But nonetheless, I think we also need to look at critiques that exist that are already kind of problematizing our existing legal frameworks. So within AI fairness scholarship, there's a lot of leaning on anti-discrimination law, but there's longstanding critiques of anti-discrimination law's inadequacy for addressing, structural racism in particular, right? So what type of legal frameworks are we going to rely on, and are we going to be aware of and sensitive to existing critiques before we try and kind of appropriate from existing legal scholarship and then try and kind of update it for the present?
Thank you.
Thank you.
All right. Thank you so much, Dr. Weinberg, for your presentation. It was very insightful and interesting. I wish we had more time because we are having great discussions, but unfortunately our time is up. Before concluding this webinar, Kelly also has an exciting announcement about an upcoming event. Kelly, could you please let us know more about this event?
Of course. So this is just to let you know that we have a conference coming up on IIT's main campus called Human AI Interaction in the Future, Values, Responsibilities, and Freedoms. This is the International Conference on Computer Ethics, Philosophical Inquiry, and we have presenters from all over the world coming to join us. We'll also have a virtual part of this conference on May 24th and 25th, and if you do register for the in-person conference, you'll also get to take part in the virtual. We'd love to have you visit our website and learn a little bit more about it. And I don't know if we have any students with us today, but registration for students who are Illinois Tech students is free. So I hope you can take part in that.
Great. Thank you, Kelly. All right. I think we can conclude this webinar. Dr. Gilpin and Dr. Weinberg, do you have any final thoughts? Sure.
No, just thank you. Thank you so much. And Leilani, thank you so much. You're brilliant and I love learning from you. And I'm just so appreciative to everyone's questions and delighted to have been invited. So thank you again.
Yeah, and vice versa. I loved your presentation, and thank you for inviting me. I think this was a really great event.
Thank you again, Dr. Gilpin and Dr. Weinberg, and thank you to all the participants. I would also like to thank the Center for the Study of Ethics in the Professions for sponsoring this event. Have a great rest of your day, everyone. Thank you.